everyone, this is Bruno. This is the third episode of the series where we're developing a sports car together while studying VI-CarRealTime. Our focus is to create a track version of a baseline car. From the work we've done together in previous episodes, the car is already a lot faster, with the components that we changed and also the detailed fine-tuning we've done using handling ISO maneuvers. In today's episode, we're gonna upgrade the aerodynamics package, using components designed to generate more downforce, which will give more grip to the car. After installing these new components, we'll analyze the performance of this package using batch simulations. This wide investigation allows us to map the performance and also optimize it by defining the ideal ride heights and rake for the car.
Without further ado, let's load our project session through the File menu and look for the Track Car Tutorial Session.xml file in our working directory. Let's also create a backup of our previous episode's car right away to keep a copy of it for future comparisons. Head into Build Mode, right-click the vehicle's main folder in the tree view and clone it. Name the clone trackcar_ep02 and select the track car database to store it in. And finally, save and delete the backup from the tree view. With this, we can edit the current model freely. The aerodynamics package we will install in our car is composed of a rear wing, a new splitter, side skirt extensions, and modified rear bumper and diffuser. With all the new components positioned, we can still optimize further the aerodynamics performance by adjusting the front and the rear ride heights, which will influence the airflow around the body. This is a powerful tool in high-performance vehicles. Typically, going as low as possible is desirable to maximize downforce and minimize drag. On the other hand, going too low may cause the car to heavily rely on the bump stops and maybe bottom out too much, both sacrificing speed and damaging the underfloor when hitting the asphalt. In order to find the right trade-off, we will run a series of tests on a racetrack. We will understand how low we should go on each axle. Let's start by preparing the car in build mode. We will be interested in ride height data for this investigation, so we will begin by calibrating our model's height sensors, so that they better reflect the visual representation of the car. If we were to run the investigation right now, we would be getting negative values for the height. The simulation would still work as intended, but we will recalibrate it so that height 0 represents that the floor is touching the ground. To do this, we'll navigate to the body subsystem, open the Aerodynamic Forces tab, and update the front sensor Z coordinate to 150 millimeters, as well as the rear sensor Z coordinate to 150 millimeters. Let's also activate the skid plates, which are points positioned with relation to the vehicle reference system, that will be able to collide with the ground, representing the car's floor. Still in the body subsystem, open the skid plates tab and activate each of them by clicking the cell to bring up the activation menu. We'll double-click the front axle and set lock Z to 126 millimeters. And also set the rear lock Z to 152 millimeter. Now, let's adjust the suspension height values to match the calibrated sensors. We can use this opportunity to also set up the suspension stoppers. For both suspension subsystems, we will visit the Bumpers tab and the Suspension Setup Data tab. Starting from the front suspension subsystem, we'll go to the Bumpers tab. Activate both Rebound and Jounce. Double-click Rebound and set bumper clearance to 40 millimeters. Now we go to the Suspension Setup Data tab and Ride Height, and set both Ride Height Sensor Z to 150 millimeters and both values of a ride height to 126 millimeters. In the rear suspension subsystem, we'll repeat the same. We will go to Bumpers, activate both Rebound and Jounce, expand Rebound, and set bumper clearance to 270 millimeters. Then we'll go to rear suspension, suspension setup data, ride height, set ride height, sensor Z to 150 millimeters, and ride height to 152 millimeters. These adjustments were made so that the ride height sensors are calibrated, while the height of the car won't change. And we can limit suspension displacement with suspension stoppers and model ground touch with the skid plates. In the same way as we do for other complex systems in VI-CarRealTime, aerodynamics are represented by lookup tables and scaling modifiers. We will define the performance of our upgraded aero package in that way. To do that, we'll select again the Body subsystem and navigate to the Aerodynamic Forces tab. We'll browse for a new property file, we'll look for the race car database and borrow its .aer file as our reference. In our case, this is just a representation. In a car design process, we would be running CFD simulations to define the aero properties for this car from a CAD model. The final change we want to do is on the visual model itself. Download the zip folder from the video's description containing the model. We recommend you extract this file in the same folder where the standard sports car graphics are stored. Now, go back to VI-CarRealTime and, in the car's body subsystem, navigate to the Vehicle Graphics tab. Disable the XGR file to enable the replacement of the individual parts of the visual model, and browse for a new body wavefront file. At the sports car database, you will find our new track car chassis model. Select it and open. Remember to save all our modifications to the model, and with this, our car upgrades are completed and it is ready to go through the aerodynamic optimization. We must create the event that we will use to investigate the performance of the aerodynamics. As usual, we'll do this in test mode. We will be testing how the car performs through a full lap on a real racetrack at full speed, so we are looking for a max performance event. If you don't have the max performance event available in your VI-CarRealTime bundle, make sure to contact VI Grade Support for information on how to get access to it. We'll right-click Max Performance in the event bookshelf and add it to a new fingerprint. Make sure the model is pointing to the track car and rename the event accordingly. For the path file, we'll navigate to the shared database and select calabogie_drv. Also look for the road data file called calabogie.rdf. We'll enable the road graphics file and find calabogie.vgf. Enable flying lap, use suspension data and tire limits in predictor. Under vehicle settings, enable update vehicle location and set it to automatic based on DRD. Let's save the selected fingerprint and run the simulation. Because of their complexity, max performance simulations may take a little longer to run than the other kinds of events we used before. When the log says it's done, we can review it in the animator to see what our current car looks like when going around a lap. Once we're done, we can close the animator as we now have everything ready to begin investigating the effects of changing the ride heights. Up until now, in this series, we studied build mode, test mode, and review mode, as well as how to plot and analyze data in VI Animator. Our work for the remainder of this episode will be focused around another section of VI-CarRealTime, the investigation mode, which is accessed through this button. Investigation mode is an environment where we study the effects we get on the performance of the vehicle when varying parameters. The first section on the top left of the screen is the fingerprint bookshelf, containing the event fingerprints we previously created and ran in test mode. If we right-click the Max Performance 1, for example, we can add it to a new investigation, creating an item for it in the investigation tree, the section below. After selecting the investigation, we can set it up in the property editor. The basic workflow around here is linear. The first step is to search the list of candidate parameters, where we find all handling variables we can investigate in this event. Let's expand the front suspension, suspension setup, left-right height sensor, right-click ride height, and promote this candidate to factor. It's now listed as one of the factors whose effects we will be investigating. Clicking on it will display its configuration options. We can rename the factor to height, front left, so that it's cleaner and easier to find in the investigation report. Here, we can select between describing a continuous variation interval or test specific discrete values. Let's leave it as continuous. Delta type let us choose how to vary the factor. We can choose to set absolute values to define the range of variation, such as if we wish for the height to vary from 50 millimeters all the way to 150. Or we can choose to set values relative to the current value of the model, in case we wish the height to vary by 50 millimeters around the current nominal value of 126. Or we can choose a relative percentage to vary, for example, 50% around the original value. Let's select the absolute delta type. For the front left height variation, let's define the lower limit to 50 millimeters, the upper limit to 126 millimeters, and set the levels to 5. These settings mean we will be investigating the effect of varying the front left right height from the current nominal height all the way down to 50 millimeters in 5 steps. Let's also promote the ride height for the front right into a factor. Rename it accordingly by calling it height front right, and let's set it up exactly as we did for the previous factor, by leaving type as continuous, delta as absolute, lower height limit at 50 millimeters, upper limit at 126 millimeters, and splitting it into 5 levels. And let's do the same for the rear suspension ride height, which is a single parameter that we will name height rear. Leave its type as continuous, delta as absolute, lower limit at 50 millimeters, upper limit matching the nominal value at 152 millimeters, and also split it into 5 levels. On the top right of the screen, we need to define the responses we want to observe when we run this batch of simulations. Click Add and select the response _01 that appeared on the list. The property editor now refers to this new item, and we can set it up. Let's select the physics output channel we want to monitor while we vary our input factors. Browse for the time, all caps, and enable it. Rename the response to lap time, and leave it to report the maximum value. Click to add another response and select it. For the physics output channel, browse for the aeroforces.aerobalance and rename it aerobalance only. Set it to report the average value, meaning we will now be able to monitor the time it takes for the test to be finished, and the average aerobalance of the car throughout the lap for the many combinations we will run. Finally, the very bottom displays the global settings for this investigation. Simulation mode is the same setting we have available in test mode that defines how and what should be run. Select Inherited from Event to use the same setting from the original event we created in test mode. You can rename the investigation's output folder here to organize your files and avoid overwriting older results. We will call this one Lap Time Analysis. The output channel map specifies the .xml file to be used by VI-CarRealTime solver when running the investigation, in case you want to change it from default or override the output map defined in build mode. We won't change this. And here we have to choose between running a full factorial investigation, meaning all of the 5 levels we defined for each parameter will be run, characterizing the complete investigation. A 2-level full factorial, meaning only the lower and the higher level of each parameter will be run. Good for when we need to have a feel for how impactful is the range we set. Or custom, allowing the analyses to be defined by CSV files. Let's choose full factorial. The last thing we will talk about before we run this investigation is grouping factors. If we want multiple factors to change simultaneously, like both front heights, we can group them together by right-clicking the factors and assigning the same group to them. Number 1 in this case. Let's also assign the rear height to group 2. The parameters within each group can be of different types, but they must contain the same number of levels. Like if we want a spring and a damper to change through a certain amount of settings together. With the groups set like this, our investigation will run 25 simulations, being 5 variations for the first group of factors, times 5 for the second group. To see the simulation plan, we can expand this menu to view its design space, a report that shows how our investigation is planned to be performed, listing all of the factor combinations that will be simulated. Close it for now. To conclude this first test, let's make sure the investigation is selected under its fingerprint and hit play to initialize the simulations. A pop-up window will display the progress of the investigation, and we can also navigate to the solver log in test mode to see how each iteration is going. The green icons beside all our pre-events and events confirm they were successful. Once the investigation is ready, let's head back to investigation mode and click on View Design Space and Results to open the report, including the simulation results, where we can notice it now displays the response values for each combination. We can already learn a few things from observing the results sheet. If we look at the lap times, we can confirm a tendency towards better performances when the car is lower, as we expected. But the relation is not simply linear. At some low heights, like in the very lowest combination available, the lap time won't get faster, suggesting something may be going on that causes inconsistencies. In this case, we know what is happening. At low heights, the car begins to bottom out at times, causing seemingly random losses of time at different points of the track. At higher height settings, the lap time variation is closer to linear, suggesting the inconsistencies are not as common anymore. The average aero balance is also very rearwards, ranging between 29 and 41% of load in the front throughout the lap, what should provide enough stability at high speeds. If we aim at a moderate performance gain, while avoiding the region where the car is too low and inconsistent, we can search the range around version 7 for candidates. If, for example, we compare version 6 to version 25, that represents the car at the original height we had before the investigation, we can see a lap time improvement of 1.6 seconds, which is a lot. Version 7 comes close while maintaining almost the same aero balance as the original height. If we scroll down a little bit, we can also find this graphical representation of the factor combinations that led to each response. For example, click the line leading to the lowest time to highlight it, so that it's easy for us to follow it and see what combination of factor settings allowed the car to perform like that. We'll be implementing version 7 to the model now. In investigation mode, right-click the investigation in the fingerprint and select the option Apply Variant. A new prompt will show up replicating the result sheet. Select version 7 and confirm. Head back to build mode, where we will notice the suspension subsystems are bold, indicating they were modified. If we navigate to the Suspension Setup Data tab in each of them, we will see the ride height values were adjusted to match those on version 7. Now go to test mode and run our max performance event once more. When the simulation is done, play it in the animator to see our car running with the new height settings. If you wish, you can apply what we studied in the previous episodes and create custom plots to observe the height readings, and even plot the bumper force metrics to observe when the suspension is hitting the bumpers throughout the lap. We could also apply other variants to our model to rerun the individual test and analyze its specific performance. If we did that to version 5, for example, we could study what caused it to be one of our slowest combinations. With the selection of version 7 though, today's development is concluded. Go back to build mode to save all modifications to the model. And also remember to save our session so that we can continue our studies in the next episode. Today, we studied how to batch run simulations to conduct optimization processes, easily trying many combinations of parameters at once and looking for their effects on a selection of relevant responses. We did that by explaining how investigation mode works. Then we set up and ran a lap time investigation to optimize the installation of a new aero package to the track car. And we also observed the investigation results report for hints about what is the best performing combination of settings for the parameters we investigated. In the next episode, we will be studying standardized ride maneuvers to define damping characteristics. I'll talk to you soon.